Okay, you know that inverter is converting from AC means DC to AC. So I told you the some of the examples of how the inverters are used in our colleges. Okay, like even in a UPS uninterrupted power supply, there is an inverter. Okay, this inverter can be used in a different form. So these are some of the things. Okay, we have seen the outlines. Okay, different outlines and the process of converting DC to AC powers. Okay, how it is used, and we have also seen the applications for high voltage. They uses this thyristor based inverters are used for the low voltage to medium voltage. Okay, for the low voltage to medium voltage, gate control turn off devices are used, like gate commutation devices are used. So these are some of the power BJTs, MOSFET, IGBT, GTO. So all these things are used in the low and medium power inverters. So in addition to the fully control, these have a high switching frequency. So these devices, okay, low to medium power inverters have a high switching frequencies. And applications, it is used on the variable speed AC motor drives, induction heating, okay, and standby power supplies, like standby is the UPS uninterrupted power supplies, high voltage DC transmission systems. So you might study on detail on HVDC system in power system, power electronics applications. So these are some of the applications of inverter, from where we can use the inverter. And it is classified into different form. This is the main broadly classified as a CSI and VSI, current source inverter and a voltage source inverter. These are both broadly classified as CSI and VSI. Or it's also known as CSI, so current source inverters is also known as a current fit inverter and also known as a current driven inverter. In voltage source inverters, or is also known as a voltage fed inverters, and also it's known as a voltage driven inverter. So on the basis of the devices used, okay, whether they use the STR or they use for the gate commutated device, like STR, if it is high voltage they use an STR, but for low and medium voltage they use this gate commutated devices such as power BJT, MOSFET, okay, IGBT. So they use this for, so we can even classify it based on the device used, and also based on the circuit configuration, whether it's a full or half or full. So based on this, it can be classified as a half or full. So other one is on the basis of the nature of the output, what type of output it's going to give. So the inverter is going to give as a square waveform as output, as a quasi square or as a semi square. So you can have classification based on the nature of the output. And other one is on the basis of the type of the circuits. What type of circuits do they use? Whether it's a switch mode or SMP switch mode power supplies, whether they use a switch mode systems, or whether they are using a pulse width modulation. We have already talked about this PWM, and whether they use a zero link converter. So there are so many classification we can do basis on the basis on the type of circuit they use. So let's see the first one, that's voltage source inverters. Our voltage source inverter can be a half bridge or it can be a full bridge. Now, what is voltage source inverter? So if we just try to see that what is voltage source inverter, is one in which the DC source has a small or negligible impedance. So the DC source has a small or it has a negligible impedance. So VSI has a steep DC voltage source at its input terminal. So it has a steep DC voltage source at its input terminal, and VSI is also classified as square wave or pulse width modulation inverter. So VSI is so usually, okay, it's a square wave. VSI is a square wave, and it is a pulse width modulation type of circuit they use it as a pulse width modulation for VSI, voltage source inverter. And for current source inverter, CSI is a FET with the adjustable current from a DC source of high impedance. So which is if it can be adjustable and it from a DC source of a high impedance from the steep DC current source. So it can be adjustable, means there can be a variations of a DC source of high impedance. So output current waves are not affected by the load. In CSI, the current waves are not affected by the changing in the load or the type of the load it varies. So changing in the loads. So used in a very high power AC drive. CSIs are used for very high power AC drives. And classification based on the thyristor based inverters. So if it is thyristor based inverter, it can be a line commutated or it can be a force commutated. If it is high power, if it is for the high power applications, so it can be a line commutated or it can be a force commutated type of classification can be done if it is using a thyristors. So you know this, what is line commutations, what is force commutations. Okay, it's a fully controlled single phase or a three-phase converter connected to a battery. Fully controlled systems either it can be a single phase or it can be a three-phase converter to a battery or a DC source act as an inverter. So fully controlled signal phase or a three-phase converter connected to a battery or a DC source act as an inverter. So when alpha is greater than pi by 2. So is a fully controlled single phase or a three-phase converter connected to. So in a force commutation, so you know in a force commutation it requires an additional circuit because you require an external circuit. Okay, you know what is force commutation. Okay, and a natural commutation. So force commutation is you require an additional circuit for commutations of a thyristors. So what type of commutation techniques are we trying to use in this one? Because commutations, you know what is commutation, right? Because in case of a force commutation, it means you are trying to force the STS to stop conducting. So you require something additional circuit, okay, just to make then STS stop conducting. So these are the following types like series inverters, parallel inverters, or auxiliary commutated inverters. So there are so many classifications. Okay, classification can be done. The inverter can be classified into so many different ways. So it's a commutating elements, inductor or capacitor. In case of a series, inverters are permanently connected in a series. So in case of a series inverter, commutating elements are permanently connected in series with a low impedance. So we'll see this later on. And parallel inverters, commutating elements are separated, which are connected in parallel with the conducting thyristors. So in parallel inverters, the commutating elements are separated, which are connected in parallel. In case of a series, commutating elements are permanently connected in series. So in auxiliary commutated inverters, it's used to commutated a conducting thyristors. Like these are examples MC Murray or modified MC Murray inverters are the auxiliary commutated inverters. So these are the some of the classifications of the inverters: series inverter, parallel inverters, or auxiliary commutated inverters. And complementary commutated inverters, this is another type, which is tightly coupled inverters are used to turn off the other SCRs of here. So in complementary commutated inverters, all this commutation, okay, because the most difficult task, okay, what I see in an SCR or thyristor is that commutations is a problem because you need to commutation means you're stopping the SS from means from conducting. You're commutating, right? You're trying to make the SA stop conducting. So it's in case of a complementary commutated inverter, it's tightly coupled inverters and it's used for the SA. Means like in case of complementary, it is used to turn off the other SCRs of the pair. So in MC Murray Bedford inverter. So the example of means complementary commutated inverter is MC Murray Bedford inverter. So there are different or means like many means like authors have those inverters they try to manufacture the inverter based on the convenient based on the requirement for the different applications. So they might have done the modification of the initially developed inverters so based on their requirement, and they might have improved the efficiency of the inverters. Just wait 1 second. Okay, sorry, there was a call. Okay, so these are some of the specifications. Now we'll straight away go to the single phase voltage source inverter. So broadly, they classified this as a single, means like VSI or CSI. If you go through the textbooks, okay, it's broadly classified as a voltage source inverter, either it's a voltage source or a current source. And there are so many that people have classified into different form based on the material, means the switch they used, or based on the output waveform. So there are so many different types of inverters are there. So in this case, okay, these two switches, S1 and S2, are the switches. Okay, this can be, or switches can be, or STR, or it can be a power BJT or power MOSFET. Whether it can be used for the high voltage applications or it can be used for the low voltage applications. Now, there are common load connected to this. But initially, this D1 and D2 do not have much function on this. But later on, okay, when the load changes, then there will be some application of D1 and D2. So if you just remember, okay, you might have seen similar type of circuit diagram in other in whatever we have covered in other units, okay, which you have covered. So there are two switches, S1 and S2, and the current flow of current, if S1 is switched on, then there will be a flow of current from A to C, as indicated on this diagram. So if you see, S1 and S2 are gate commutated power semiconductor devices. So these are gate commutated, means that it's for the low and medium power inverters, and it can be a thyristor for the high power applications. So it's mostly it's a gate commutated power semiconductor where the switches are, these are the switches. All with whatever we are talking, okay, till now in power electronics, okay, it's just a switch. We are talking about the switch, whether you are converting from AC to DC or DC to DC or AC to DC to AC. We are just talking about how are you how do you control the switches? Either we need to switch on or off. So based on the convenience of what is our desired output, okay, based on this we can fiddle with these switches. So it's just a switch. The output will mainly depend on the switches only, means like the output of the switch, either which are switching on or off. So when closed, this switches conducts and current flows in the direction of the arrow. So when it's closed, so the current will flow from A to in this directions, as shown in the. So in case of a resistive load, when the switch S1 is closed for the half time period T by 2, so when this is closed in case of a resistive load of a desired AC output, so it connects point A to DC source of point C. This will connect to point C, so the current will flow in this direction when S1 is closed in case of a resistive load, and the output voltage will become equals to V by 2. So output voltage will be, so this is a period where waveform of getting a signal one, when the switch is, when you trigger this, is means first when this switch S1 is conducting, then it will conduct, period will be T by 2. It will be T by 2. So the output T by 2. So at T by 2, getting signal is removed from S1, it turns off this S. So if it is getting signal is removed, and when this is off, then there will be, it will turn off. At T by 2, getting signal is removed, and from S1, then it turned off. So this is what is happening. So T by 2, so during up to T by 2 it is conducting, then again there is another cycle of T by 3 T by 2. So this is the waveform of getting a signal for switch S1. So for the next half time period between T by 2 to T, getting signal is given to S2. So in that period, the getting signal is given to S2 at that particular period. So next half. So it connects the points B to of a DC source to a point C. So this point B is connected to point C in another half. In the first half, this S1 will connect, and in another half S2 will connect. So it connects, so then the output voltage will be reversed. So at this period the output voltage will be reversed, that will be minus b by 2, thus closing the s1 and s2 alternative. It will not close at once, okay, it will connect in alternatively for half time period. A square wave AC voltage is obtained at the output. So this is when the s2 is closing. So in the positive half, this s1 this is conducting in other, and the s2 is conducting, then this portion t by 2 to t is conducting on this particular. So for the resistive load, the load current will be v naught by r. So diode d1 and d2 does not play any role in this case if the load is purely resistive. So the frequency will be equals to 1 by t. So it depends on the total time period, how much, how at what period the S1 is switch on and at what period S2 is switch on. So this is how it's. So this is a total voltage when S1 is conducting. The switch S1 is conducting. This is the period when this switch S1 is conducting during the positive half. So at one half this switch S1 is conducting, so the voltage will be V by 2. So during the negative half, the voltage will be minus V by 2. So if you see S2 is conducting, the voltage will be minus V by 2. So if you want to find out the current, V equals to IR. So you have I equals to V by R. So this you can find out the current from this. Alternatively, S1 and S2 is conducting. So the drawbacks is as a lesser efficiency. Efficiency is quite low in case of a half, means in case of this single phase voltage source inverter, that's half bridge. In case of a half bridge, the efficiency is low. It requires 3-wire DC supply. So in this case, it requires 3-wire DC supply. So this is the case when the current and voltage waveform, when the load is RL. Initially, if you remember, the diode D1 and D2 do not have a function. Now in this case, diode D1 and D2 has a function in this case. So D1 and D2, when the load is raised, RL load. So in this case, D1 and D2, these two has a function if the load is RL load. So when it is RL load, so it is divided into 4 mode of operation when there is RL load. If you, in case of R load, is quite simple. It conducts in a positive half cycle. S1 conducts in positive half cycle, and during other means like the other half, S2 will conduct. But if you see here, if the load is RL load, now the effect of L. Okay, now in this case, it is divided into 4 mode of operations. We'll come to this waveform. So in mode 1, during the time 0 to when the time t is equals to 0 to t1. So during the time when time is equals to 0 to t1, this is the mode 1 operation when d1 is conducting. In this case, when 0 to time period is from 0 to t1. So getting signal is removed from S2. In this case, gate signal is removed from S2 and is turned off. So it means that at this point, S2 gate signal is removed from S2 and this is turned off. S2 and is turned off. So in this case, at this instant, load current is at negative peak. So if you see here, the load current will be at negative peak, minus I naught. During that period, when the gate signal of S2 is removed, and the load current will be at a negative peak, minus I naught. So at this instant, load current is at negative peak from the previous cycle, because at that point we have gated this signal. S2 is removed at this point, and the current becomes negative maximum. If you see from this waveform, you'll see that current is a negative maximum negative at this point. So current cannot reverse instantaneously. because of the inductive nature of the load. So because of the inductive nature of the load, current cannot be reversed at this point. So a path of a negative current is provided as a feedback to the diode D1. So feedback is provided on this diode D1, which is forward bias due to reverse of the voltage across the inductor. So in this case, so it is more than V by 2 at t equals to 0. So it is more than V by 2 at t equals to 0. So at this point, D1 is conducting. So a negative current is provided by the feedback diode, which also D1 and D2 are the feedback diode in this case. So the voltage will across the D1 and to keep this voltage across D1 is to keep this S1 in reverse bias conditions. So this will remain in off state even though the gating signal has been applied. So even if the gate signal has been applied, so at this point, now this is the point, okay, at t time period t equals to t1. So during the interval between 0 to t1, the load voltage is positive, but the load current is negative. So load at this point from 0 to t1, load current is negative. If you see here, it will be maximum negative current to the current will be reached up to this point at t1. But if you see here, the voltage will be positive at this point at mode 1. So energy will be stored on the inductors. It means inductors. So there will be the switching diagram is already shown to you. Okay, that there will be feedback to the upper DC sources through the D1 and load current will decay on this case. So this is a switching diagram of mode 1 operations when S1 is closed. Okay, at this point, because of the current, because of the inductive nature of the load, you have RL load. So this D1 will conducting. It will also conduct at this particular point. So this is a point when 0 to T1 at the mode 1 operations. And in mode 2 operation is from T1 to T by 2. Mode 2 is T1 to T by 2. This is a point when S1 is conducting. At this T1 to T by 2. At this point, both the current and voltage will be positive at mode 2. So D1 will be commutated in this case in mode 2 operations, and S1 will be turned on. The switch S1 will be on, and current through the load will build up to positive direction. So if you see here in the waveform, the current is building up to the positive, means in positive form. So during the interval, V0 and I0 are positive, and the energy is stored in the inductor. So in this case, V0 and both the I0 and V0 will be positive, and the energy will be stored in the inductor. Switching diagram is shown out here. So at this point, S1 is conducting. If you see G1 is also off. So in the previous case, G1 is conducting, S2 is off. Right? In this case, S1 is conducting, and if you see a switching diagram, this is in mode 2 when S1 is conducting. In mode 3, it's T by 2 by 2 T2. So if you see here, T by 2 to T2, this is the point in mode 3 operations. So S1 is turned off. In this case, this switch, this will be turned off in mode 3 operations. So current is positive maximum, and it cannot reverse instantaneously. So current becomes maximum at this point, and because of the inductive nature of the load, current cannot be reversed instantaneously in this case. So G2 is forced to turn on to carry the positive load current. So in this case, G2 is forced to turn on at this point. So at this mode 3, G2 is on. D2 is forced to turn on. So D2 is on, the load current will decay and become 0 at t equals to t by 2. So if you see from this diagram, it decays to t by 2 at this point. It will decay at this point, T by 2. So load current will become 0. So during this interval, okay, negative load voltage will be negative and the current will be positive. So energy is released by the inductors and is fed back to the lower DC source. So this is a switching diagram for mode 3 operations. So in mode 3 operation, D2 is conducting at this point. In mode 4, at T equals to T by 2, so D2 is commutated and S2 is turned on in this period. So that D2 is turned off and S2 is turned on at this point at T by 2 to T during this interval. So time T is equals to T by 2. So current through the load builds up in reverse direction and it becomes maximum, negative maximum at T equals to T. The switching diagram is already shown here. So at this point, S2 is conducting during mode 2 operations. So I'll stop here. Okay. So I'll continue in the next class. Okay, on this class we'll talk on single phase full bridge inverter with R load. Okay, so please start preparing for the phase test. So your phase test will start from 6th. As per the we are given this from 4th to 16th, but it will means as per our timetable which we have done. Okay, draft timetable it will start from 6th to 16th. So at least you will have 1 day. Okay. So please study and take care. Bye.
Thank you, sir.
Thank you, sir.